That was the old way of getting rock strength. Let me show you the new one. For this presentation, we will go over the objective behind this project, how this study is significant to geological studies, how this project was conducted, and what we found. The main objective of this project is to understand the relationships between rock strength values and physical characteristics of sandstones in the Upper Cretaceous Woodbine Group, located in the East Texas oil field. So why should we care about this project? Well, for starters, it addresses an intersection between geophysical and geological studies that is lacking in understanding, specifically correlating different physical properties of a sandstone with rock strength values. This study also represents a brand new exercise in rock strength calculation through the use of a micro-rebound hammer, which provides data at a much higher resolution and allows for the preservation of core samples, which would otherwise be destroyed from conventional means. Finally, understanding different variables that affect the strength of the rock is one of the fundamental steps in determining the manner to which rocks break during processes like hydraulic fracturing and horizontal drilling. So how was this project conducted? First, we selected core samples that displayed contrasting physical characteristics such as different sediment facies and permeability. Next, we measured the Lieb's hardness value of the sample through the use of a micro-rebound hammer. Finally, we determined the unconfined compressive strength, or UCS, of a rock based on the previous measurements. Here we have the micro-rebound hammer. This device strikes the core with a metal bit, which rebounds back after striking the core and provides the Lieb's hardness value of the rock. Once we have acquired the hardness measurement, we convert that value to our final goal, unconfined compressive strength, which represents the material's ability to withstand stress without failure. This concept is displayed in the figure to the right, where the conventional rock strength test used pistons to apply pressure to the core sample until it breaks. This example relates back to the significance of using the rebound hammer as a means of preserving core samples for future use. Now on to our final results. This first figure represents the UCS values of the B2 Killingsworth core. Looking at this figure, we can see that the yellow sandstone layers present medium to low UCS values ranging between 20 to 60 MPa. The gray mudstone layers in the lower section display higher UCS values of over 100 MPa. Finally, if we look at the middle of the section, we see a large series of conglomerates, which display the lowest UCS values ranging between 0 to 40 MPa. From this figure, we can conclude that the different fabrics and facies of a rock do have a dramatic effect on their strength. Here we have a much deeper core known as the Blackstone. Compared to the Killingsworth, we see that the average unconfined compressive strength has increased to much higher values beyond 100 MPa. This section presents lower permeability as a result of an increase in cementation concentration throughout the sandstones, which result from being buried at this great depth. This indicates a positive correlation between the cementation of a rock, the permeability, and its rock strength.